So, good evening again for those of you who've joined us from this part of the world, and good morning if you're in the western coast of the US. This is the third episode of Meet the meQuanics, and we've got a bit of a schedule change today. Unfortunately, Chad Rigetti couldn't join us today because of a different scheduling conflict. Hopefully we'll have him on sometime in the future. However, luckily enough, we've got Rod Van Meter from Keio University, who has graciously agreed to push up his appearance on these little web episodes and come in and talk to us about where he fits into the quantum world and why he got into it and exactly where he thinks things are going. So Rod, thank you very much for coming at very, very short notice today. And thanks for staying up so late.
Hi, thanks, Simon. I'm happy to be here. It's a good thing we had already discussed having me come in and do one of these things, but we hadn't set an actual date. So from my point of view, it worked out just fine to have Chad not be able to make it today so that I could step in and do it. We'll have a good conversation here, I think.
Yeah, I think so. So basically, the first thing I try to approach this is to ask people exactly, how they got into this and exactly what they're working on. So you're sort of, we had Austin Fowler on last week, who's technically a theorist, but he now works for an experimental group. But I suppose you're probably the first real theorist that we've had on this. Well, at least as somebody who's still working in theory, somebody who's not tied very specifically to an experimental technology. So I suppose you come very much from the classical side of things, at least that's your background, and then you sort of merged into quantum. So basically, why'd you start working on this stuff?
I'll tell you a story. So I've collaborated a lot with Thaddeus Ladd, and he referred to me as a theorist one time, and I said, don't refer to me as a theorist. If you try to compare me to other theorists that I'm never going to look good, because the theorists are very, very mathematical and very rigorous people. But instead, I'm actually an engineer. And Thaddeus said, "Oh, come on, you've published papers in Physical Review, right? So when you submitted them, did you check the box that said theory or experiment?" Like, well, I guess I'll take the Fifth Amendment on that one. But you're right. My background is actually in classical computing systems. It's not in quantum mechanics. I'm not an experimental physicist or a theoretical physicist, either one. I've spent most of my career working on classical systems, operating systems, computer architecture, especially storage systems and networking. And I decided in 2003 that it was time to try something that had the potential for extremely high payoff, even if that meant doing something that was pretty risky. And I spent a bunch of time looking around, thinking about what I wanted to do, considered DNA computing and analog computing and a couple of other things. And I settled on quantum computing as being the single most or largest payoff concept from among all of them, out of the things that I looked at. Mm-hmm. I knew then that it was risky and that it was far off. I had people tell me, "Oh, you just don't have any idea how far off it is yet." I said, "Oh, come on, we're going to need all kinds of engineering skills involved in the process of designing this. Give me a hand up and we'll get started on it." And now it's 13 years later, and in particular, I would say, yeah, my point of view was kind of naive when I got into this in 2003 in terms of the set of problems and advances that would need to be made in order to actually realize quantum computing systems. But I was absolutely right that there are a lot of engineering-oriented problems that have to be solved in doing this, and I'm really proud of the things we've done in the last dozen years and think there's still a lot of interesting work for us to do. But especially in the last 2 or 3 years, there's been tremendous experimental advances, and the experimentalists have started coming to us and saying, now we've conquered more or less how to build 1-qubit and 2-qubit systems, and we have no idea how to build large-scale systems. So I'm looking forward to helping the experimentalists actually build those large-scale systems.
So what's your primary focus? I mean, do you focus on any given system, or are you sort of all over the place, or are you really just trying to sort of push the physics community into, you know, this stuff has engineering constraints, this stuff is now moving into, you know, the regime of like classical computing, classical telcos, and, you know, you need to be thinking like an industry. I mean, do you have a particular focus, or you just sort of go wherever the field pushes you?
Well, the earliest work that I did was all very abstract and not tied to any sort of particular physical implementation. It was done at the level of qubits and gates, and actually originally with only a very limited focus on error correction as well. But within the first few years, it became really clear that one of the most important areas we could work on contributing to was how to actually implement error correction on systems. And so we actually got heavily involved into things like the surface code, which you and I have worked on, and Austin and I have worked on, and Thaddeus Ladd and I have worked on together over the last several years. So in that sense, it's not been tied to a particular choice of technology. It's not been tied to quantum dots or superconducting qubits or all photonic systems for the most part. But some of the specific papers we've written have been in conjunction with experimental groups that were trying to figure out where to go. In particular, the group of Yoshi Yamamoto, which is how I worked with Thaddeus Ladd and Cody Jones, and we did a couple of papers together on quantum dot architectures and what it would take to actually build surface code error correction based systems on top of that. I'd say a lot of our approach has been trying to figure out how to apply the principles of classical computer architecture to quantum computing. Mm-hmm. The questions on how you build a system are still the same, and the principles that you apply are still the same. But of course, the parameters that you plug in are very different, because the behavior of quantum systems is very different in terms of how fast they are, how big they are, what their weaknesses are, and what their strengths are. And so the ultimate designs you come up with, I think, will be very different than classical computing systems, even though the underlying principles that you build on to get there are the same.
So, I mean, you see a pretty strong analogy with the development of, especially in quantum communications, so the classical internet and the classical data networks that we see now that form the foundation of the internet, and what could happen quantumly. I mean, are there any significant differences, or do you see the technology really following sort of the same kind of timeline? It just happens to be different kind of technology.
That's a good question. So of course, there are differences. One of the biggest differences, of course, is the difference in behavior of quantum systems, in particular quantum communication systems, that they don't use the same kind of store and forward mechanism that classical networks use, particularly that the internet uses. It's more of a distributed set of operations across an entire group of quantum nodes in your quantum network that are collaborating to build a shared quantum state over the course of it. And so in that sense, the fundamental underlying model of what it means to communicate in a quantum system is different from the way it is in a classical system. In a classical system, it's the implied semantics of giving somebody a message or an internet packet is, please send this on to the next person for me that will get it toward the destination. But in quantum networks, I think the core underlying semantics are, please help me build this shared state. And I think that results in a rather different set of protocols when you're actually starting to build the network.
So in that particular sense, you think that everything will have to be restructured from the ground up, or you can take, you know, sort of the fundamental structure that already exists and just map it to this new type of technology?
Well, we're doing our best in our group on the networking side to actually build on what we've learned in the 45 years of internet-related development, the understanding of how to build networks and then take collections of disparate networks and combine them together into what we call an inner network. And in the process of doing that, we're actually trying to apply the principles from internet community, and also even such factors as trying to figure out what the behavior of large-scale networks will be based on the topology of how the links are set up. And that topology, we don't have any other basis for how we think it might be organized other than to sort of model things on the way that the classical internet's actually been built. And given that the research group that I work in at Keio includes some of the best internet people on the planet, the people who brought the internet to Japan 25 years ago, those senior professors are kind of always on my case and on the case of my students. Why do you think this is a good model? Why do you think the quantum internet will actually develop in the same way? And so they always sort of keep us on our toes to make sure we're working from a valid set of assumptions and exploring the space broadly enough that even when things do change or don't come out the way we anticipated, that ultimately the answer we produce will have some sort of validity or the ability to work across a variety of potential environments for both deployment and technology.
Well, that's a good point in the fact that you say you work with people who sort of brought the internet to Japan. It's kind of an interesting argument as to how you push this, considering I imagine that when they brought the internet to Japan, you know, there were computers, there were communication networks. As primitive as they might be, they existed.
Yeah, absolutely.
But now you're trying to push into a field where arguably no equivalent technology actually exists. The very best, there's like a half a dozen qubits sitting in a couple of labs in the world. So, I mean, how do you make this case?
That's actually a really good question. So to sort of answer that, I guess I got to give you a little bit of the history of my group, I guess, and sort of talk about that. For the first several years, after I got into this field, I really concentrated on quantum computing, on how to take quantum algorithms like Shor's algorithm and actually execute them on some sort of quantum computer that we might potentially someday be able to build, how to actually execute error correction efficiently, what the resource requirements are of the system, what the demands are that are made on the underlying technology.
Mm-hmm.
I did that for maybe the first 3 or 4 years that I was in the field before I ever even touched or thought about quantum networking. But at some point, we got interested in networking, and I did some work with Kai Nemoto and Bill Monroe, people that you've worked with. Your collaboration with Bill and Kai is one of the reasons that you and I know each other. I guess we actually first met each other through Kai.
Yeah, I think so.
She had a project on quantum repeater networks that she involved me in, so I did some of the simulation work with that alongside Thaddeus. He and I developed a quantum simulator together. And part of the reason for me to be interested in that was, at the time, it seemed like quantum computing systems, large-scale quantum computers, were very hard and the challenges were tremendous. And it seemed like quantum networks had the potential to be simpler and easier to deploy with the technology, and that we would be able to deploy them alongside the classical internet and use them to provide services to computers on the classical internet. And so it seemed like maybe we can do networking first before we get to quantum systems. Now, I think a lot of people think that's sort of naive, because for quantum networks, in fact, each node on a quantum network is actually going to be a lot like a small-scale quantum computer. So you're talking about having to be able to build quantum computers and connect them together over long distances. So you're taking full quantum computing technology and then adding something on top of it. So now it seems like the prevailing view is that maybe quantum networking is actually harder than quantum systems. I think that's a view that a lot of people have, but it's not really one that I agree with. I still think there's a good chance that it's going to be easier to deploy quantum networks than it is to actually deploy quantum computers. But that'll have to be done with sort of a limited view to what the quantum network actually does, rather than using them to connect large-scale quantum computers together. It would be used to provide a specific set of small-scale services to classical computers to augment the kinds of things that we do in the classical internet.
So such as what? I mean, what do you envisage small-scale quantum networks actually doing?
Well, the first obvious application of quantum networks, and here, everything I've said so far, I'm really primarily talking about entangled quantum networks that build on top of what we call quantum repeaters. The first obvious application for that is really quantum key distribution, which is an extension to what we do today with single photon quantum key distribution using.
So I suppose the distinction sort of has to be made is that when you say sort of an entangled quantum resource, so what is that?
So in that case,
I mean, what are we communicating when you say we're sharing an entangled quantum resource in a quantum communications network? I mean, it's not the same thing as a classical network where you fire a light pulse down an optic fiber that carries a bit string and you're done.
Right. So again comes back to the semantics of what I was talking about a minute ago, where I said that the fundamental semantics of what happens on a quantum network is not really transmitting a message. It's really building a shared quantum state. And in this case, what we're talking about is building entangled quantum states. Now, entanglement's this concept where two quantum subsystems, two variables, or two quantum bits held in two different locations share a single state in a way that's not possible classically. And what you get out of that is some interesting behavior. This is what Einstein famously called spooky action at a distance, where actions on one of these, well, let's use the example of qubits. Let's assume we're talking about you and me sharing a qubit between,
I think it's the simplest example,
our house and our apartment here across Tokyo. If we're sharing a pair of qubits that are actually entangled, when I look at my qubit and measure it, I can then learn something about the state of your qubit that you're holding across this distance without any sort of intervening classical communication. So we share an entangled state some way before we execute this communication, and this state may be that both of our qubits are in the same state. So when I go and measure my half of our shared state, I might get a 0 with 50% probability and a 1 with 50% probability. So I might have a state where mine is in this state that I can't tell what it is until I go measure it. But once I've measured it, I'll get this random result out of it, a random classical result, and I'll know that yours is exactly the same as mine was. So if I get a 0, you get a 0. If I get a 1, you get a 1.
So now, you can communicate fast. So you can communicate faster than light. You can go as far as you want.
Sure, sounds good, right? That's what worried Einstein about this when this notion of entanglement first started developing in the 1930s. Well, if this is true, then something must be happening. It must be possible for people to actually communicate faster than the speed of light by doing this. Well, it turns out that's actually not the case. So it becomes a shared source of randomness. You and I will get the same value, but we can't actually use that to exchange any sort of message between the two of us, other than something that was already agreed on beforehand.
So it's randomness, but we have the same randomness.
Right. It's randomness, and we have the same randomness. And it's not something that allows us to actually send a message faster than the speed of light. So it turns out that the correct interpretation of Einstein's theory of relativity is not that there's no shared effect across a distance that happens faster than the speed of light. The correct interpretation is that you can't send information faster than the speed of light.
Mm-hmm.
And so what happens with this state is once we measure it, we've each got this random bit, but we can't do anything with it that allows me to decide to tell you whether we're going for sushi for lunch or whether we're going for pizza for lunch.
Mm-hmm.
Other than if we had already previously agreed on some sort of protocol, like if it comes up 0, we're going for sushi, and if it comes up 1, we're going for pizza. But I can't use it to tell you that the result of the baseball game that I can see that you can't see, or something like that over this time. And this correlation for this entangled state is stronger than what happens classically, because we can use it to, we can actually measure the state, not just in this 0-1 basis, this 0-1 pair of values, but we can actually measure it in several different ways. And that kind of correlation will actually show up in those several different ways. And part of that falls out of actually the mathematics of entanglement and the mathematics of quantum mechanics, where rather than simple classical probabilities, what you actually have in the state is actually quantum amplitudes, which are actually complex numbers involving imaginary numbers, the square root of -1. So that thing that everybody in high school mathematics really hated. Come on, imaginary numbers. What are you talking about?
Well, now it's actually being applied to technology.
Yeah, it actually exists in quantum mechanics. It shows up in a lot of engineering problems, so it's a useful technique in any way, shape, or form. But what's happening is this imaginary nature of the phase of a shared quantum state actually gets us some of this entanglement. That's sort of mathematically where some of it falls out.
So give me a bit of a flavor, sort of, the state of the art when it's coming out of your group, when it's coming out of Keio, when it's coming out of Aqua. Where are you now? What is the pressing concerns that you have in terms of your work?
Well, hang on. Let's go back. Let's roll back to one question and finish the question we started with a couple of minutes ago. So we were talking about applications of quantum networks. What are the kinds of things you do with quantum networks? The first thing I suggested is that with these entangled quantum networks is that you can use them as a substitute for the single photon quantum key distribution stuff that was developed by Bennett and Brassard in the 1980s, and which you can actually go out and buy products for today from one of several different companies. So that's one application. There is not just that one, but a set of cryptographic applications, including a substitute for the classical functionality for what's called Byzantine agreement, which is a way to help us build secure fault-tolerant systems. There's a set of applications for distributed sensor networks, and those distributed sensor networks include techniques to use entanglement to synchronize clocks better than the precision of atomic clocks. So that's one area. There have been several different protocols proposed by that, including by Misha Lukin's group from Harvard, and one by Ike Chuang, and one by Richard Joza.
So sorry, you synchronize multiple atomic clocks to get better accuracy than just a single quantum atomic clock?
Well, it's synchronization of the clocks across a distance. So if you use the entanglement properly, in theory, it's possible to synchronize your clock and my clock to a higher precision using entanglement than we could achieve just using classical signals between you and me.
Mm-hmm.
We want to have our clocks be exactly the same. Now, whether that can be achieved in practice to higher precision than the precision of the classical supporting hardware we have to have in order to make the quantum systems work is still kind of an open question. There's a lot of detailed engineering work that has to go in there in order to figure out what the precisions of the relative components are going to be and whether or not we can achieve this in practice. But the mathematics falls out nicely. It looks very nice on paper.
Right.
So that sort of ties your earlier question about applications for distributed entanglement to your new question about what are the kinds of things my group is working on. That's one of the kinds of things we're working on, is trying to figure out how good communication systems are going to have to be in order to actually do something using a quantum network that doesn't have a classical equivalent.
Right.
The algorithms exist in theory. There have been any number of papers published describing distributed quantum algorithms for doing things, and we're looking into the engineering of what it will take to actually build those. And it's a wide open area. It's something that people really haven't done yet, with the exception of the case of quantum key distribution.
Sure, but I mean, distributed quantum computing is pretty far in the future. I mean, it doesn't just assume the existence of quantum computers. It assumes the existence of a lot of quantum computers and arguably a communications network that's even more complicated than quantum computers. So,
right.
I mean, is there stepping stones except for QKD and things like that? Is there something that, is there something you can look to that sort of, this is the killer app?
That's what we're looking for in distributed networks and distributed quantum computing systems, is what's that killer app besides QKD? Now, QKD, in theory, you don't have to have anything except a very small 1 or 2 qubit quantum computer at each one of these nodes. And so on paper, it looks attractive relative to the idea of having to have million qubit computers or billion qubit computers, which is part of why we were interested in being able to deploy these quantum networks initially. Mm-hmm. Now, the question is, does the engineering hold up? Can you really achieve it with such small-scale systems? And are those small-scale systems actually easier to deploy than large-scale systems? It depends on some of the engineering questions, like how much cryogenic support hardware you need in order to make the nodes operate properly, or engineering constraints like that. So mm-hmm. Will it be possible to deploy quantum networks in a simpler fashion than it is to deploy a set of quantum computers? I think that's sort of an open engineering question. Mm-hmm. But the corollary question is there a killer app that can be achieved with modest capability nodes in the network that will allow us to build the quantum network alongside the classical network and deploy it in a useful way? And we think so. We've been doing some interesting work on quantum Byzantine agreement, for example, and looking at that. So there's the cryptographic functions, the sensor network functions, and then on down the road, true distributed quantum computation. So that distributed quantum computation is something equivalent to the very earliest days of the ARPANET, the predecessor to the internet, developed in the late 1960s and early 70s. The goal for the ARPANET was to allow people with very small or limited computing resources to connect across a network and connect to a mainframe or a large computer or a large data system somewhere else in the country or somewhere else in the world and be able to use that system remotely. We'd like to be able to achieve the same thing with quantum networks. And so the true distributed quantum computing is the end goal, but we know that's still a long ways away. It takes mm-hmm. large-scale deployable quantum computers to actually get there.
So where do you see, I suppose this is the question that I'm asking everybody, well, I mean, where do you see the situation is right now in terms of not only where the technology is, where the hardware is, where the software is, where the theory is, but also in terms of sort of private versus public? We're seeing stuff moving into places like Google, IBM, moving a little bit out of the academic space. Do you feel that this is an appropriate time for that to happen? Or, just generally, where do you see the field sitting right now?
I think it's fantastic that we're developing really the early stages of a quantum computing industry. I can name a dozen companies startup companies that are involved in the field in one way, shape, or form. There are about 5 or 6 companies that are doing quantum networking, mostly doing still single photon BB84 quantum key distribution. And I can name 5 or 6 companies that are trying to build actually large-scale quantum computers. And that's even discounting the rather substantial investments from Google, Microsoft, and IBM using their own money. And there are many other of the large companies around the world are executing research projects, in some case with their own money, in some case with money that's coming from government research grants.
Mm-hmm.
And as we've seen in the UK with the development of the UK's technology hubs last year and the year before, there are people who believe that quantum information technologies are reaching the point where it's time to look at tech transfer. It's time to figure out how to take this stuff out of the lab and put it in the field and start developing products that people will see a reason to actually buy and
Mm-hmm.
actually put money into. So I think we have startups, we have the large companies involved, we have significant money from governments involved in tech transfer, and we have also seen in the last couple of years development of a couple of venture capital firms that are planning to invest a couple of $100 million US in startup companies. So the ecosystem is starting to develop.
Sorry, a couple of $100 million of VC money into quantum startups, or just startups?
Yes, into quantum startups.
Into quantum startups, okay.
Yeah. The set of investments they've made so far, I think, is still sort of limited, but I think we'll see a lot more over the course of the next couple of years. So the technology is starting to be there in terms of the physics. 2015 was a fantastic year for the experimentalists, both pushing toward quantum computing systems and also toward quantum communication systems.
Mm-hmm.
There were fantastic demonstrations of the existence of this entanglement that we talked about for several minutes to really high precision, and so that foundation has really been laid for how to actually create and use entanglement, both for computers and for networks, I think. So the technology is starting to be there, the business and financial infrastructure is starting to be there, and the set of applications that we need in order to actually achieve market pull is still one of the areas where there still needs to be a lot of investment. And there are people who are out there working on that, and it's an area, I think, where there's still a long ways to go. But you'll hear some people talking about very big picture stuff when they talk about quantum computing.
Mm-hmm.
In particular, one of the areas that people are very interested in for an application is replacements for quantum chemistry. So to be able to solve quantum chemistry related problems at high precision for a reasonable investment of computing resources, rather than having to have billion-dollar supercomputing facilities in order to do it. And if you can solve those kinds of things, then you can get into designing materials, and you can get into designing drugs, and you can do all sorts of things. So you'll sometimes hear people talking very, very big picture stuff. This is how we actually have a positive impact on humanity, is by actually doing problems in that sort of range. And so I think there's lots of possibility that's out there.
Mm-hmm. And so where does Japan fit into all of this? I mean, most of the major investment we see, at least publicly, is very concentrated in Europe and the US, and a little bit in Australia. But how's Japan moving forward? Are they moving forward on this, or are they lagging behind? Are they far ahead?
Japan has a number of really leading edge experimental groups. Nakamura-san's group over at the University of Tokyo is certainly one of the leading groups in superconducting qubits. There are others in the country. Akira Furusawa's group, also at the University of Tokyo, in quantum optics. So experimentally, there are groups in Japan that are among the world's best. And the Japanese government's been very supportive. They've put a lot of money into this. In particular, how long ago has it been now? I guess it's been about 6 or 7 years ago. They started a project called the FIRST project, which was a large-scale investment by the Japanese government into supporting about 30 faculty members across Japan, and I was one of the faculty members who was supported. I got some of the money in that just as I was starting as a professor, and so it really sort of helped establish my career in that sense. So I would say the Japanese government was a very early investor at relatively large scale in terms of public investment in this. We're all looking forward to what the next large increment is from the Japanese government, but the individual professors that I know have been very successful in terms of getting competitive funding from the Japanese government through the Japan Society for the Promotion of Science and other Japanese government agencies. So I think right now there is good money from the Japanese government, but right now there's not one single large-scale project, one sort of national-scale effort. And I'm not plugged into the right group of people to know if there are currently negotiations going on to actually do that next kind of national stage project or not. You know, the government is always sort of carefully choosing what is going to invest in.
Right. So on a more personal level, where are you going next in terms of your group, in terms of your work in the next, 3 to 5 years? I mean, this is what I've been asking of all my guests: is what do you think you can do, and where do you think the field is going to be in 3 to 5 years?
Well, I guess now is the time for a public announcement. Just earlier today, I got word that I was funded by the Japan Society for the Promotion of Science for the next 3 years to work on applications for distributed quantum computing. So we're going to try to be analyzing a set of these distributed quantum applications that I was talking about in detail for which ones can be implemented on achievable network test beds. So what's the smallest size quantum network at which we can actually try one of these applications? So quantum key distribution exists already. What's the next application we would actually do on a test bed quantum network if we have one? So to me, that's a problem that I thought was important enough that I proposed it to the Japanese government, and they said yes. So that's now going to be one of the largest focuses for me in the next few years. There's still a lot of work to be done on engineering of large-scale quantum networks, as opposed to just figuring out how to connect two nodes together. There's still a lot of work on how the networks will evolve over a period of time. Like the classical internet that exists today, there's technology that's on the network that's been running since the I don't know about the 1970s, but certainly since the 1980s. There are computers that are that old that are still connected to the internet today. And so how will that same kind of evolutionary path work in a quantum internet? That's one of the areas we've been working on. So I think that's very important. There are questions about the robustness of quantum networks, how easy they are to disrupt the operation of. Will it be possible to build a robust quantum network? I think that's an important one. So a lot of the problems that I'm looking at are engineering-related problems on quantum networks. In terms of quantum computing systems, like I said, a lot of our work over the last decade has been on how to implement error correction effectively. And we've been producing some interesting results, and we've got a couple more coming out soon, I hope. You and I are in the process of editing up a paper with one of my students with some results that I'm really pleased with. We'll see if they hold up as we finish the editing on the paper in terms of how to implement the surface code on a system that's less than physically perfect, and a system that might actually be physically buildable. I'm not talking about the error rates of the individual quantum states, but more which parts of the system work properly and which parts of the system don't work properly.
Yeah, it's the thing on dead qubits. You fabricate something, it just doesn't work.
Right. In classical systems, when you fabricate a computer chip these days, almost every transistor on that quantum chip actually, or on that classical chip, works properly. But there's been a tremendous amount of work done in fault-tolerant systems and figuring out how to actually build systems that work even when some of the components don't work properly. And none of that has been done in the quantum domain. There's been a lot of work that's the equivalent of error correction for transmitting signals. What happens when a state gets corrupted as the state goes through space or through time? If you're trying to hold a state for a period of time, what happens when the data gets corrupted? But there's been very little work on how to deal with systems that are defective. And I think that's an area that actually needs a lot of work. I'm really happy with the results we've got. I think there's more that we can do. The next step after that is really to begin working in more detail with the experimental groups and say, okay, everything we've done so far is at the abstract level, independent of what your actual physical implementation is. Now, how can we map that to a particular physical implementation? What does it tell us about what the experimentalists need to achieve in order to be able to make the systems work? And are there shortcuts or optimizations we can do based on the particular technology that will allow us to do things more efficiently? So I'm looking forward to working more with the experimentalists on what we're doing for error correction.
So you sound like you're pretty optimistic. This stuff's going to happen. It's not a question of if, it's a question of when.
I have believed all along that the technology is achievable. Whether the systems actually reach the level at which they are interesting in a commercial sense kind of remains to be seen. But I believe the technology is fundamentally achievable, and I've always sort of believed that. My earliest interest in this whole field began when I was actually an undergrad at Caltech in the early 80s. I actually managed to take a class from Richard Feynman, who everybody loves to cite Feynman because he was so incredibly charismatic and funny. But he's often cited as one of the founders of the field of quantum computing because of some of the work that he was doing at that time. I didn't have anything to do with the work that he was actually doing then, but he taught us about reversible computing and taught us about a lot of different aspects of underlying physical systems, and that interest kind of carried me forward over the course of time. So I like to think about sort of what's fundamentally achievable in terms of physical computing systems, and I still think that quantum computing systems are achievable, and even if they don't become commercially viable, what we're learning in the process is going to be incredibly important for the next generation of computing systems, one way or another. So I have no qualms at all about getting students involved in this, and I have no qualms at all about working in the area. I'm convinced that what we're doing is going to matter.
And I think we're hitting on 45 minutes. I think that is a good note to end that on. Certainly a level of, yeah, I think certainly a level of optimism is definitely warranted in every one of these conversations. So obviously, thank you, Rod, again, for joining us in this little episode and being one of the first to participate in what I hope is going to be a sort of ongoing set of discussions with any quantum researchers that I can get on the phone for half an hour or 45 minutes, and especially for jumping in at the last minute because of our other cancellation. So stay on the line afterwards. I'll have a bit of a chat after we go offline, but thank you again.
I got to say, congratulations on getting the meQuanics thing, the whole meQuanics thing started. I'm optimistic about seeing good results out of that. I think it's very cool what you're doing with that.
No, good luck with it. Thank you. So, for those of you who've joined us live, thank you again for staying up late if you're in this part of the world, or for getting up early, or being up in the middle of a workday if you're in other parts of the planet. We will continue this series, obviously. as soon as we have somebody confirmed next from some other research group, some other part of the world, keep checking out the meQuanics Twitter feed, keep checking out our Kickstarter page for updates, and obviously this YouTube channel, and we'll let you know as soon as the next event is scheduled, hopefully sometime within the next 5 or so days. Obviously, this series, Meet the meQuanics, was inspired to help promote the Kickstarter campaign for the meQuanics game. There is a link in the low bar down below for those of you who would please like to spread the word or donate yourself. That would be awesome. For those of you who are interested in quantum computing, obviously my contact details are all over the place. As part of this video, I will also link to Rod Van Meter's group at Keio University. Anyone who is interested in doing work on quantum, doesn't matter what your background in, physics, mathematics, computer science, there's always a project for you. I'll put a link down in the low bar for his group. If you're interested in his work, get into contact with him. I'm sure now that he's got this new funding, there might be some avenues for collaboration and research. So thank you all again.
Definitely looking forward to it.
Yes. So for those of you who joined us live, thank you again. And those of you who are watching offline at some later date, keep checking out our channel, and we will continue updating with new interviews as they come along. So thanks all again. Cheers.